Welcome, this is Coach Dorf. Today we're going to talk about the fundamental theorem of calculus, part 1. To do this, let's start with an example. Suppose I have a number, we'll call it x here. If I add 6 to it, I get x plus 6. Now, if I take that new number and I subtract 6 from it, what do I end up with? I end up with x. Not a big surprise, but we started with x, we ended up with x. We ended up with the original number. This is because addition and subtraction undo each other. They're inverse operations. All right, let's look at another example. Suppose I take the number u and I multiply it by 4, I get 4u. All right, and if I take that 4u and divide by 4, what do I end up with? I end up with u, which was my original number. All right, that's because multiplication and division are inverse operations of each other. They undo each other. Now, this is nothing new to you. This is like, duh, Coach Dorf, this is really obvious. All right, but this is the idea behind the fundamental theorem of calculus. That is that just like addition and subtraction undo each other and multiplication and division undo each other, in calculus, derivatives and integrals undo each other. That is the idea of the fundamental theorem of calculus. All right, let's look at it formally now. So here are the hypotheses of the fundamental theorem of calculus. I have a function f that is continuous on a and b. Next, I have this function g of x, which equals this integral from a to x of f of t dt. Let's talk about what g is. What does that represent? Well, if I have a graph here, and let's just draw a function, we'll call this one f. All right, and I'm going to have a value a and b. All right, what does g represent? Well, remember the integral can be thought of as the area under the curve. So the lower limit on the integral sign, this a here, is going to be the starting point. So I'm going to have my area under the curve here. And now x, this number in gold here, that is some variable that changes, and x is somewhere between a and b. So I'll just like put it in there. So there is x, all right? Then the integral here that's given in number 2 represents this area here, that area. That equals g of x. And as I move the gold color x, as I move this here back and forth, then my area is going to change. That is my function g. It represents the area underneath it. All right. The third condition is that g is continuous on that closed interval from a to b, and it's differentiable on there. So that means that we don't have like any sudden increases in the area. So the area doesn't go from 1 and then jumps to 2. If it did, then the function g wouldn't be continuous. Okay, but instead, when we say g is continuous, it's slowly increasing in the area there. It doesn't make a sudden jump. And it's also differentiable. All right, those are the hypotheses of the fundamental theorem of calculus part 1. And then what's the conclusion? The conclusion then is that the derivative of g equals f. Or if you want to think of it in this terms, and it may be more helpful to think of it, that f equals the derivative of the integral of f. So that you can see I've got derivatives here, and I have an integral here, and they undo each other, and they end up with what I started with. Now, some of you may say, well, wait a minute, what you just circled, has a t in it, it's f of t. Well, that t is like a dummy variable, okay? Nothing personal against t's, t's are great, okay? But it's just a placeholder, that t is a placeholder. Really, the variable here is this x here, and that represents this x there, okay? So t is just a placeholder. I do this integral, and when I do this integral, then I'm going to put in an f of x here, and that's why I get f of x. So this is saying that if I take first the derivative, and then after that, or sorry, if I first take the integral, okay, the inside, and then I take the in green, and then I take the derivative in purple there, I'm going to end up with what I started with, which was my function f of x. That's the fundamental theorem of calculus part 1. That is really cool. It really is. Okay. Feel free to clap or, um, show some excitement in your house as you're watching this or wherever you're watching this. Okay. But hopefully you're not like driving and watching this at the same time because I don't want anyone to get into an accident. Okay. So let's look at how to apply this to some specific examples. All right. So here I've got this problem. It says find the derivative of g. And now g represents an integral. Remember that integral is like area under the curve. So I'm taking the derivative of an integral. All right, so let's look at the solution. So I want to find g prime, which is going to be the derivative of this integral from 0 to x of the square root of t cubed plus 1 dt. Remember that this part here, the t is just a placeholder, a dummy variable. All right. Well, what does the fundamental theorem of calculus tell us? All right, we have it circled up here at the top in red. It's saying that if I take the integral first, and on my integral, I have a constant. This is any constant. In this case, in this example, it's a 0. And in the top here, the top integrand is the variable x. The variable x, which is the variable of our function here. Okay. Then if I do that integral and then I take the derivative, I get back what's in red. And what I'm going to have to do is then replace the t's with x's because that is my variable. The t's are just a placeholder there, but when I take the derivative of it with respect to x, I have to put in the t's. I mean, put in the x's for the t's. And so I end up with x cubed plus 1. And the square root of that. That is my answer. That's all it is. Okay. So again, just to show it really quickly here, if g of x is this integral from 0 to x of the square root of t cubed plus 1 dt, then the derivative of g is just going to be x cubed plus 1, the square root of that. That's it. All right. Isn't that simple? Isn't that cute? All right. Let's look at another example. All right. Here's a problem. I want you to stop the video for a moment and solve this problem by yourself before I show you the answer. Stop the video. Okay. I'll give you a few seconds. Stop that. All right. All right. Now, hopefully you've stopped it. You solved it. Let's look at what you get when you do this. I'm going to use the fundamental theorem of calculus. I notice this is a constant number. And this is my variable x. All right. So by the fundamental theorem, this derivative here of this integral from 1 to x of the square root of t over t plus 1 dt is just going to equal the square root of x over x plus 1. That's it. Really sweet, cute. All right. All right. So now, of course, as you know in math, things can get a little bit harder. So let's look at a little bit harder example here. All right. Example 3, find the derivative of this function, which I have the integral from x to 1 of cosine square root of t dt. Now, you might think to yourself, okay, well, how is this different than the previous one? Well, what's different is I've got my 1 at the top and I've got my x at the bottom. And the fundamental theorem of calculus says we know what, sorry, let me redo this. Fundamental theorem of calculus says we know if I have this, and I take the derivative of that, I'm going to get back the cosine of the square root of x. But that's not exactly what we have in this problem, right? Here, the 1 is on the bottom and x is on the top, which is what we're supposed to have. But in the original problem here, the limits on the integrals, the numbers or the terms on the integral sign are backwards. So how can we fix that problem? Well, we can do the following here. All right, we can say g of x equals the negative of this integral from 1 to x cosine square root of t dt. All right, using the fact that if you switch the limits on the integral sign, you just put a negative in front of it. All right, and because of that, then we use the fundamental theorem of calculus at this part here, and we get negative of cosine of square root of x. Okay, because again, I have a constant here in the lower limit, and I have my variable x in the upper limit, and so I use the fundamental theorem of calculus, and I just replace the t's with x's. All right. Notice I don't have to like find the antiderivative if some of you are thinking that way. Okay. I just take what I have here, this function here, and replace it and put it over there and replace the t with x's. As long as I have the same setup as in the theorem for the fundamental theorem of calculus. All right. Okay. Let's look at another example here. All right. Here we have my function. It's the integral from 0 to 1 over x arctan of t dt. So some of you may like first look at this and you'll say, oh no, we've got an arctan. I don't remember any of those formulas for arctan. That's okay. You don't need to know them, right? Because we're using the fundamental theorem of calculus part 1. All right. We're just going to replace the t's with x's as long as we start with the form that we're supposed to have. Here's the difficulty though, right? I don't have that form, right? If we had this, like this, then I could use the fundamental theorem of calculus, and it would just be arctan of x. But that's not what we have. Instead, we have this. Instead of having an x like up here, we have instead a 1 over x. How does that work in? Hopefully this is not a big surprise. We have to use the chain rule because we're doing derivatives here, right? We're taking the derivative of the integral. Well, by the way, I guess I made a mistake here. Let me just fix one mistake here. What I have here is this is d dx of that. Okay, by the fundamental theorem. Okay, I'm taking the derivative, right? This is what I'm doing. I'm taking the derivative. So I've got to apply the chain rule. All right. So how does that work? Well, I'm going to take the derivative, d dx, of the integral from 0 to 1 over x arctan of t dt. Well, by the fundamental theorem of calculus then, what I'm going to get is the arctan of x. Whoops, sorry, not x. Let me go back here. What do I have? I want the arctan of 1 over x, because I'm going to replace that in here for t to get that. But I'm not done, because then I need to multiply it by d dx of what I had here. And this is where the chain rule comes in. All right, so I have arctan of 1 over x times the derivative d dx of 1 over x. And what is the derivative of 1 over x? All right, well, let's just do that off to the side here. So the derivative of 1 over x. Some of you I know have this memorized because you've done it enough, but just to show all the details here, I write 1 over x is x to the negative 1. I use the power rule. I get negative 1 x, and then I reduce the exponent by 1. So I started with negative 1, reduce that by 1. So negative 1 minus 1 is going to be negative 1x to the negative 2, which is the same thing as negative 1 over x squared. So I have the arctan of 1 over x times negative 1 over x squared. That's my answer. Okay, so even though we don't have this, this is a 1 over x instead of an x there, I can replace the original amount from the fundamental theorem of calculus part 1. Instead of having an x there, I can replace it with any function as long as I use the chain rule in doing that. All right. So let's look at another example here. All right. I want you to try this one. So I want you to stop the video, try doing this one yourself. All right. So I'll take a moment, stop. Okay, now welcome back. We're going to solve this one. I am expecting that you stop the video and you have an answer for this. Even if it's not right, even if you're not sure, this is a way you'll learn better by doing this on your own first before you see the answer, okay? So we're going to take, I've got this function here, the integral from pi over 4 to the square root of x, theta d, theta times tangent of theta d theta. Again, now, instead of using, earlier we used the t's, but here we're using a theta, okay? It's just a place value, a variable, it doesn't matter. What matters is really what I have here and here. So first of all, this has to be a constant. It can be any constant, it doesn't matter. And pi over 4 is a perfectly valid constant, all right? This has to be a function, okay, of x. So I have to have something with x's in there. If it's just an x, then I can apply the fundamental theorem of calculus very easily to just replace the thetas with x's, so I would get x tan x. But it's not just an x, it's a square root of x. So we have to use the chain rule. So what do we get? So I'm going to take the derivative with respect to x of the integral pi over 4 to square root of x, theta tan theta d theta. Okay, and so by the fundamental theorem of calculus, part 1, call that 1 there, I'm going to replace every theta, okay, with x in this function here. Okay, the d theta just tells me that I'm integrating with respect to theta, so theta is my variable in the integral sign. So, but I'm looking at the red part, that's what's important. So when I do that, I'm going to get, replacing the thetas with square root of x, so I get square root of x tan square root of x, all right? And then I have to take the derivative of the square root of x by the chain rule. This is, again, the chain rule. Keeps coming back. All right, and so what is the square root of x? Again, some of you have done it enough that you already know this, but if you're not, let me just detail it out. I would write x to the 1/2 power, and now by the power rule, I bring the 1/2 out front, I write x, and I subtract 1 from the exponent, so it's 1/2 minus 1, which is going to be 1/2 x to the negative 1/2, which is the same thing as 1/2 1 over x to the 1/2, which is the same thing as 1 over 2 square root of x. Okay, so what I get here then is the square root of x tan of the square root of x times, by the chain rule, the derivative of the square root of x, which is 1 over 2 square root of x. Okay, now I can simplify this because I notice that there's a square root of x there and a square root of x there. And if this were a multiple choice question, I would expect that the answer would have something, it would look something like this, tangent of square root of x over 2. Okay, let's look at this example. If this had been, it's a very basic problem to take the derivative of that with respect to x and use the fundamental theorem of calculus, and it would just be x squared over sine of x plus x squared. That would be it. But that's not what we have, because this is different than what I have up here. So we have to change this. So what do I notice? I look at my original function. I'm going to circle this in blue. I'm going to take the derivative of that. So what about the limits on the integral there? Well, I have an x squared in the bottom, and in the top there I have a 0. So first of all, they're backwards. All right, so I'm going to write then that the integral uh, from x squared to 0 of t squared over sine t plus t squared dt is going to be the same thing as the integral from 0 to x squared of t squared over sine t plus t squared dt if I put a negative in front, right? I can switch the limits on the integral if I put a negative out front. All right, and now I can take the derivative of what's on the right side using the fundamental theorem of calculus part 1 and the chain rule. All right, so what do I end up with? Let's use the color purple. All right, sorry for the reference there, for those who got that one. All right, so the original problem I want is the derivative of the integral from x squared to 0 of t squared over sine t plus t squared dt. And I'm going to first rewrite that as the negative integral from 0 to x squared t squared over sine t plus t squared dt. So I'm going to get the negative. And when I take the derivative, I apply I apply the fundamental theorem of calculus. So fundamental theorem of calculus part 1. And I'm going to replace all the t's here, okay, with the x squared. So I'm going to get x squared squared in the numerator because I have a square there over sine x squared plus x squared squared here. All right. And then by the chain rule, I need to take the derivative of x squared. All right. And so then I have, let's simplify this a little bit. I've got negative x to the fourth on the top over sine x squared plus x to the fourth. And then the derivative of x squared by the power rule is just 2x. And then I can combine the x to the fourth and the x next to the 2x to get negative 2x to the fifth over sine of x squared plus x to the fourth. And that's my answer. Let's look at this example here. Now I've got this integral from tan x to x squared of 1 over the square root of 2 plus t to the fourth dt. So the thing to notice here is that I've got a tan x here as a limit on the integral sign and an x squared. So I have no constant. So how can I insert constants into this? Well, we're going to use a property of integrals. And that property says that the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. All right. And so the key thing here is that this and this are the same here. And then I've got my a like here, and I've got my b up here. And you can think of this if we were to do this in terms of like a function graph here. If I did, here's a, here's c, and here's b, then this integral, this integral in green represents this area. And this integral in red here represents this area. And the integral in purple represents the area of the green plus the red. And that makes sense that that would work. All right, so we're going to use that idea to rewrite this integral. So I'm going to have g of x equals the integral tan x to x squared of 1 over square root of 2 plus t to the fourth dt. And I want to write that as two separate integrals. So I'm going to have tan x here, and I'm going to have a box up here, 1 over square root of 2 plus t to the fourth dt plus the integral, and now I have a box up here, and I'm going to have an x squared up here with the same integrand, the same function after the integral sign. And so these boxes I'm going to do in red here are like my C's that I did up earlier. And I can place them now. I can place anything in there, any constant, and I'm going to put in a constant 0. I could do anything I wanted to. I could put in a 1. I could put in 269. I could put in pi, anything I want. I'm just going to put in 0. Okay. And now the second integral here is set in the form that I can use the fundamental theorem calculus and the chain rule to find that derivative. The first one here in green is not quite like that. I have the 0 on the top, the constant on the top, but I can just switch that by doing a negative. And so that's what I will do. So I will just say that this is equal to the negative of the integral from 0 to tan x of 1 over the square root of 2 plus t to the fourth dt plus the integral from 0 to x squared of 1 over the square root of 2 plus t to the fourth dt. Okay, so when I take the derivative here, g prime is going to equal the derivative d dx of the first integral, 0 to negative of the integral of 0 to tan x of 1 over square root of 2 plus t to the fourth dt plus the derivative of the integral from 0 to x squared of 1 over 2t plus t to the fourth square root of that dt here. Whoops, I think I have a little mistake there. So let me go back a little bit. Yeah, okay. That should just be 2 plus t to the fourth square root dt. Okay. All right, and so now I just take the derivatives here. So I'm going to, this negative is just a constant, so I just put that out front. And now I take the derivative of the integral, and by the fundamental theorem of calculus, that's going to be 1 over 2 plus tan x to the fourth under the square root, okay, because I'm going to replace this t with this tan there. All right. Then by the chain rule, I have to take the derivative of tan x. Then plus for the second one, I'm now going to replace the t there with an x squared to get and 2 plus x squared to the fourth under the square root, 1 over that, all right, times by the chain rule, the derivative of what's in purple, the x squared, to get that. Okay, so then I have that blue here. What is the derivative of tan x? So just as a review, derivative of tan x is secant squared x, and the derivative of x squared is 2x. So applying those, then I'm going to get negative secant squared x over 2 plus tan fourth x square root plus 2x over 2 plus x to the eighth square root. And that is my answer. Okay, so we did several examples like that. I think those covers a lot of the cases that you need to see. So let's do one last problem here, kind of talking about some of the ideas of what the fundamental theorem of calculus represents, or fundamental theorem of calculus part 1. So again, in the theorem, we let this function g equal that. And just as a review, I mentioned this earlier, but just as a review, what does that g represent? Well, if I have my function here, and this is my f here, and I'm going from a to b, and x is some number in between there, then what I get for g is it's this area. So that area under the curve equals g of x. And as, use this, as this x changes value, okay, if I move the x to the, in this case, if I move the x to the left, the area decreases. If I move the x to the right, it increases. That won't be true for every graph, but it is for this blue f that I've drew in here. Okay, so that's what G represents. It's the area under the curve F above the x-axis, starting at A and going to X, where X can change. We just have X's between A and B. All right, so let's discuss that in terms of this. So I'm going to let G of X equal this integral from -3 to X, where F is this red function whose graph is shown below. So let's deal with some questions here. All right, what is G of -3? So I should think of this. G is the area under the curve. So G equals area under the curve, starting at -3 and going to X and above the x-axis. So what is G of -3? Well, if I start right here, what's the area under that curve? Well, it's 0. Okay, because this is just going to be the integral from -3 to -3 of f of t dt. And because the numbers on the limits are the same, that's going to equal 0. All right. How about, so that's letter A. How about letter B? What is G of 3? So again, G is the area under the curve. So if I look at those two curves there, I'm going from -3 to 3. Well, from -3 to 0, I've got that red curve that's above the x-axis. And then from 0 to 3, I've got the red curve under the x-axis. And they're supposed to represent basically the same image, just kind of rotated. So if I add up the area from -3 to 0, it's a positive area because it's above the x-axis. But from 0 to 3, it's the same amount of area, but it's below the x-axis, so it's negative. So I should get for G of 3, it should equal 0, because the part from -3 to 0 cancels out with the part from 0 to +3, because they're the same area, but one is positive and one is negative. All right, let's estimate. So we've got that. For part C, estimate G of -2. Well, -2 is right here. So I want the area under that curve there. So I've got something like this. Well, that's kind of like a triangle. The base of that triangle is 1, and the height looks like it's about 2. So I would say G of -2 is a triangle. So 1/2 base, which is 1, height is 2, and so I would get 1. So G of -2 is approximately equal to 1. What about G of -1? All right, well, now I'm going from here to there. It's kind of still like a triangle, not quite, but we're just estimating the area. So we'll just say it's a triangle. The base there now is 2, and the height looks to be 3. So 1/2 2 times 3 would give me 3 for that. And lastly, G of 0. All right, so I'm going over here. It looks like I'm adding on this extra triangle here. All right, that I drew in purple. So it's going to be the area of the blue triangle, which we just figured out is 3, plus the area of the purple triangle. And the purple triangle is going to be a triangle of base 1, height of 3. So I'm going to get here, first of all, the 1/2 2 times 3, which we did in the previous part, plus 1/2 the purple triangle, which is 1/2 times 1 for the base and 3 for the height. So I'm going to get 3 plus 3/2, okay, which if I simplify that, I think I get 9/2 for that. Okay. All right, so that's letter C. Letter D, on what interval is G increasing? So again, if I think of G as being the area under the curve, where do I always get positive area? Well, if I'm starting at -3 and I go to the right, I'm going to keep getting positive area until I hit 0. Because from -3 to 0 for x values, I'm always above the x-axis. So I'm going to have the interval is what an interval is G is increasing. It's increasing from, let me just put this here. This is increasing on the interval from -3 to 0. As soon as I go past 0, so I get a number larger than 0, my red curve goes below the x-axis, which gives me a negative area. So then it starts decreasing in value because I'm adding a negative area to it. All right, so that's letter D. Letter E, where does G have a maximum value? Well, it has its maximum value at G of 0, because it's always increasing from -3 as x increases until I get to 0. After 0, then the graph goes below the x-axis, so the area under the curve starts becoming negative, and so it starts decreasing. All right, then let's try to sketch a rough graph of G. So how do I do that? Well, let's see. So I've got these values here: -3, -2, -1, 1, 2, and 3 here. And we'll use a purple color here. So we figured out some of these values already. At G of -3, we got 0, right? That was just here. And at G of 3, it's also 0. That's what we got here. And then we estimated some values. G of -2 is about 1. So let's see, let's just put these in here. G of -2, we said is 1, so that's about here. G of 1 was 3, so that's about here. And G of 0 is about 4 fifths. Sorry, is 9/2, which is same as 4.5. So I have something that looks like kind of like this. And I could do the same thing on the other side, and I'm just going to it's going to be kind of symmetric and go down like this. So there's a rough sketch of G, okay? Not of F. So what we had up here above earlier in red, that's F, right? That's F there. But in purple down here, we've got G. Okay. So now we've done letter F, and use F now, what we just drew here, to sketch the graph of G prime. All right, we did this some earlier when we were talking about derivatives. Okay, so I could look at the slope of the tangent line here at each of these points. Okay, and do that, and I get these. And what's happening to those slopes of those tangent lines? Well, it's going to look something like this. So I have, first of all, some positive values, and the positive values are increasing. Let me just draw in some numbers here: -3, -2, -1, 0, 1, 2, and 3. And I'm just going to put in 1, 2, and 3 here. So I'm looking at my green values here. My slope here is increasing. It's increasing, increasing. And then when I get to x equals 0, it's 0, the horizontal line. And then I've got negative slope, and negative slope. Okay, and it looks kind of like that. All right, so this represents G prime. Well, how does that compare to F? Well, it's actually the same. G prime equals F. Why is that? That's because of the fundamental theorem of calculus. All right, part one, because if I take the derivative of, g, I'm going to get back the original function f. Okay, because what I'm doing is I'm taking the integral of f, I'm finding the area under the curve, and then I'm taking the derivative of that. And so the derivative of the integral undo each other, and I get back what I started. All right, so what's the main idea here? The main idea is that the fundamental theorem of calculus, part one, shows us that if I do an integral and then I do the derivative, they undo each other and I get back the original function. Next time, we'll talk about the fundamental theorem of calculus part two. And what does that say? It says if I do the derivative first and then the integral, I will get back what I started with. And by combining the fundamental theorem calculus part one and part two together, it shows us that derivatives and integrals undo each other, just like multiplication and addition, just like multiplication and division undo each other, and addition and subtraction undo each other. Okay, that's a lot of ideas, but I hope this video helps clarify what we're talking about. Have a great day. Thanks.